Oh, we have a crowded room. So without further ado, let me introduce our speaker. Today we are very honored and pleasant to have Professor Yi Wu visiting us from Tsinghua University. Yi is a longtime friend. We were working together almost 10 years ago at UC Berkeley. At the time he was
really 10 years ago.
Really 10 years ago, yes, 2014. So he was visiting UC Berkeley at the time when I was also a postdoc in the same group, in Stu Russell's group. And then Yi later joined the Russell's group as a PhD student and continued there, finishing PhD from UC Berkeley. And during his PhD, he got the Best Paper Award from NeurIPS. That's probably your first NeurIPS paper, right? Second, okay. So that's an example of how you start your PhD. And after that, he joined OpenAI, working there for a year, and then returned to Tsinghua. Now he's an assistant professor in Tsinhua's Institute of Interdisciplinary Study, also known as Yale College or Yale class. And I want to mention that Yi actually made a lot of contribution in terms on the topic of Bayesian inference, probabilistic programming, reinforcement learning, and more recently about reinforcement learning training for a large language model. We are reading multiple of his papers, and he's going to talk about some of this today. So without further ado, let's welcome Yi.
Thanks, Lei, for the introduction, and very happy to be here to talk about recent works on reinforcement training for large language models. Can you hear me? Is like, well, my sound too low, or because it's a big room?
A little bit louder.
Okay. I'll try to speak louder. Okay, so today we'll talk about reinforcement training for large language models. So reinforcement learning and language model has been there for a very long time. It's been like individually developed for a very, very long time until ChatGPT. In 2022, this phenomenal applications come out, and then people noticed that, okay, reinforcement learning can really make a big change to large language models. Can really make GPT-3, which is a language model there for many years, and then turn that to a historically successful application to everyone can use. And after that, a lot of other companies like Anthropic, follow the trend of training large language models with reinforcement learning. And also OpenAI use reinforcement to enhance their safety capabilities. And more recently, OpenAI launched the reasoning specialized model 01. So there are lots of progresses based on reinforcement learning. But very unfortunately, all those big progresses are largely made by the industries and not released to the community. So in this talk, we want to raise the questions from an academia perspective, right? Can we zoom in the training process and to understand how to really make effective reinforcement training for large language models? And hopefully this talk can give you some insights and draw the inspirations so that we can have future good research on this topic. Okay, so before we start, we'll talk about the formulations of reinforcement training. So in reinforcement training for large language models, so we have some assumptions, right? So we'll have a base language model. We'll have a data set, which is typically a set of prompts, or sometimes we also have the solutions or the feedbacks. So data set. And also you have a reward model. And also based on this reward model, you will fine tune this language model eventually to get a reinforcement trained model. So in this talk, we will not talk about, so assume all these three things are given in a prior. So we are not talk about how to collect data. We're not talk about how to train a reward model. we'll primarily focus on the training process. So it's the reinforcement training process. So in a nutshell, it's basically you ask the model generate a bunch of responses, and then query the reward model, query the given reward model to get some rewards for your generated responses, and then you will apply a training algorithm to process this rewarded trajectories to get some gradients to update the model, and you keep this repetition, and eventually get a final trained model. So we'll just focus on this training process, and typically we'll think about 3 questions. So first questions, the algorithm part. So what kind of algorithm should we use to update the language model weights? Second question, right? So given the reward model, how to make best use of this reward feedbacks from the reward model? And third one is how to implement an efficient training pipeline to run the reinforcement training. So some people may ask, okay, you know, all these questions are super trivial, right? It looks trivial. You know, we seems to have answers to all these questions. But in this talk, I will say that, well, although these questions looks trivial, but there are a lot of tricky parts, and we really need to pay attention to. Okay, so here's the topic, here's the overall of this talk, and we'll go through each of these questions. So first question, algorithm part, so what is the most effective algorithm to choose to run reinforcement training? So this talk is our ICML paper this year. It's called DPO superior to PPO. So in this talk, we'll talk about whether we should use DPO or PPO to train our language model. So before we start, as a recap, so there are a bunch of ways to run reinforcement training for language models. So one very popular way is called a reward-based approach, which is mostly PPO or PPO-based algorithms. So this approach is adopted by OpenAI. So in this framework, you firstly train a reward model based on some feedback responses. You learn a model. And then the second step, you train the large language model based on the feedback from the reward model. So it's an iterative loop. So then you will run some PPO training objective, which is basically maximize the cumulative rewards with a KL constraint to constrain the policy not to be far away from the base model. So this is reward-based approach. But also, you know, for a very long time, people like to use reward-free approach. So this approach also adopted by Mistral AI and some other institutes. But mostly, it's the most representative example is DPO. So DPO is like much simpler. So instead of training a reward model, you don't need reward model anymore. You just collect the preference data set. In a data set, you have prompts, you have preference, good response, bad response, and you basically just increase the probability of the good responses and decrease the probability of the bad responses. So you will have some objective like this, some contrastive like objective like this. So, you know, there are 2 kinds of approaches, and which kind of approach should we use, right? So reward-based or reward-free based, reward-free. You know, there's a pros and cons, but most of the academia, you know, for a long time, academia people think, or academia people tend to use reward-free based approach because reward-based approach is super expensive, and sometimes it's hard to tune and give you very marginal improvement of all the baselines. So, you know, for reward-based, lots of although it's adopted by OpenAI, but there are lots of complaints about reward-based model. Particularly, it's very expensive to run, you know, and a lot of people complain that because you additionally learn a reward model, so you may suffer from the reward misspecification problem because you may have some errors in the reward model, and the training policy may amplify this reward bias. Okay, so a lot of complaints. For reward-free model, right, it's very lightweight, so easy to tune, and so easy to run, very lightweight. And also, people think lots of the academia state-of-the-art results are achieved by DPO algorithm. The question here is, although DPO is very lightweight to run, it's very simple, it's easy to tune, does it really avoid the reward misspecification issue, right? So here we'll show some example that maybe DPO may also suffer from similar issues and it may have some even more severe issues. Okay, to support this, we'll consider a very simple counterexamples that DPO may fail. Okay, so consider a prompt. Who won the World Cup 2026, right? So this event has not happened. Right? So the best answer should be, I don't know, because if you don't, it's not happened yet. So assume you have a pre-trained model, right? You have a pre-trained model, which is because Argentina won the World Cup, the previous World Cup. So you have 70% of chance predicting the token Argentina, and like 20% chance say, I don't know, and 10% chance saying Spain, because Spain won the Euro Cup. Okay, then, let's run DPO, right? You have a trajectory, a preference data set, which is essentially one sample, which is good sample is, I don't know, bad sample is Argentina, right? And then you run DPO, increase the probability of I don't know and decrease the probability of Argentina. And then you can very likely get some result like this, right? You increase the probability of I don't know to 40%, but decrease the probability to 1%. But unfortunately, the probability of Spain also increased to 50%, right? In this case, if you draw a sample from this fine-tuned model, you will have 50% chance the model just say Spain. And sometimes you call this phenomenon hallucination. Right? I would say that this is a very simple example, and there can be even more severe, more extreme examples that DPO failed. So suppose you have a base model. You have 3 different kinds of tokens, Y1, Y2, Y3, and Y1, Y2 have probability of 50%. And then you have a preference data set saying that Y1 is good, Y2 is bad. You can sometimes even have a fine-tuned result or something like this is even the probability of a good example can decrease to 10%. And the Y3 can have a probability to like 90%. This is even worse. Why? You'll say that, okay, we have an objective, which is increase the probability of good example, right? But if you really examine the objective of DPO, you'll find that the objective is essentially the ratio between the good example and the bad example. So you only worry about the ratio. So I can decrease the negative example a lot to increase the total ratio, right? There's no guarantee of whether the good example will really increase or not. So, well, you may ask, right? So why would such failure happen for DPO? The simple answer is because there is a OOD, out of distribution token Y3, right? So Y3 is not covered in the preference data set, right? And there's no guarantee of the value of Y3 will be in a fine-tuned result. And some people may claim, may say, okay, maybe let's collect a larger preference data set. But this is a large language model. So you can't really cover all the possible tokens. And this is why after DPO training, sometimes you can always see the model collapse or model just predict some very unexpected output tokens because there are some OOD tokens and you have no control of these tokens. So, okay, the natural question is, will PPO fail in this case, right? The short answer is no. PPO does not fail. It just successfully aligned the model. And why, right? So the question is, what are two different situations? The first one is if you have an accurate reward model. So if in this case, PPO is good because PPO is its own sample algorithm. So if the probability of OOD token Y3 is very high, when draw a sample from this trained model, you will draw samples. You will draw a lot of samples from Y3, and the reward model will give you a feedback saying, okay, Y3 is bad, and then you're good, right? Because it's an online algorithm, so you draw samples from the model, so this is good. Some people may say, okay, what if the model is wrong? What if the model is inaccurate? For example, we have a model like Y1 is reward of 10. Y2 is 0, and for the OOD token Y3, the reward model also is misspecified, and then you may have a reward say 100, right? Well, in this case, can PPO still succeed? The answer is yes, because you have a KL term. So KL term is, so essentially PPO have an online estimation of the KL term. So in the original base model, there's 0 probability of Y3. So if you have an online estimation of the KL regularizations, the KL regularization will give a very strong constraint to prevent Y3 to be very high. So the KL term also help you prevent the model outputting very OOD tokens, even if the reward model is wrong. So we have a very informal, well, this is an informal theory, but we have a formal one in the paper. So we have some theoretical analysis. So essentially, intuitively, is saying the solution space of PPO is a subset of DPO. Well, this is kind of intuitive because for any PPO samples, you can always construct a training set for DPO, and so you can produce the same answers as DPO. So that's saying, because people complain that PPO suffer from the reward misspecification issue, but now PPO has the solution space of PPO is a subset of DPO. That means DPO will also suffer from that. Even worse, PPO, the reward issue comes from the reward model, so you can have a hope, right? The misspecification issue only influences the reward model, and the policy may be good, right? But for DPO, if you have made any mistake, it directly influences the policy. So you should be careful. Okay, so this is a theoretical analysis, very, very informal. We also run some empirical experiments. So we choose a data set called SAFE IOHF. This is some data set with 2 kind of metric. One is safeness, one is safety. The other one is helpfulness. You want the response of the language model to be safe and then to be helpfulness while keeping a safe response. So we try a bunch of algorithms. So we first run SFT, and we run based on the base model. So if you run SFT and DPO, you will find that DPO improve the safety and helpfulness, but only a little bit. Okay, so the question is, we know the limitation of DPO because of OOD tokens. Okay, but can we, with this insights, can we improve DPO by properly handling these OOD outputs? So we propose some techniques. So first one is to run additional SFT iterations, right? Because we know that one limitation of DPO is that the OOD token can have very high probabilities. And the good examples the probability of a good example may decrease, right? So in this case, we can run an additional SFT iteration on the good examples. In this case, to increase the probability of the desired tokens. And then in this case, it really helps. It helps the helpfulness, and also helps reduce reduce the helpfulness, harmfulness, and also improves the helpfulness. This is first the technique. Second one, you need to clean the data set really carefully, right? So we can see a lot of noises and contrast controversies in the data set. So if you really clean that, it also helps improve the DPO quality. But also, just a final remark, sometimes if you over clean the data set, it may lead to some very conservative behavior of the model. So sometimes the model may just always say very safe responses without giving you any information. So when you clean the data set, you need to be careful, but this is the trade-off. The third solution is, we say that PPO is good because it collects online samples, right? So you can also do that with DPO. So you can run online generations and use a reward model to get feedback to reconstruct a preference data set every iteration for DPO. So if you do this, you keep doing iterations, you can find that the DPO performance can keep increasing as you just iteratively run that. So you can run iterative DPO, which can be a very strong baseline for the model. Okay, so we talk about how to improve DPO. Then, what about performance in PPO, this online algorithm in this benchmark? So this is the result of DPO, and we run PPO. And you can find that if you properly tune PPO, it just substantially improves everything. Okay, so then the question is, why, some people always complain that PPO doesn't work, right? So what are the key factors to improve PPO? What's the key factors to make PPO really work? right? We have 3 suggestions. First suggestion, you need a large batch size. Okay. So, so we tried batch size 64, 128, 256, 512. Just like as I said, you just increase the batch size and just the performance just keep going up. Okay, so you do need a large batch size to make PPO work. Second thing, another trick is advanced normalization. This is a very typical trick in reinforcement learning, but may not that familiar with NLP people. So, so we do that in a more competitive benchmark. Is coding, competitive coding experiments benchmark. So you can find that in the coding benchmark, it's more challenging. And if you run large batch size with advanced normalizations, you can have a 2% improvement over the baseline, over the code contest experiment. This is the second suggestion. The third suggestion is having exponential move. Instead of having a very static reference model, you can have an exponentially moving average of the reference model. So you can keep the reference model slightly moving up. So this trick is also typical in reinforcement learning. For example, in DQN or DDPG, you have a reference, the target network also moving is exponential moving average. And also in the vision representation learning community like MoCo, right? You also have this kind of trick. So this trick is to stabilize training, but also ensure the model can keep moving in the desired direction in a more aggressive way, instead of having a static reference model. So if you have everything all together, you will have finally overall the best model on the safety benchmark, on the coding benchmark. Eventually, we have a main result. Okay, question.
Quick question. So here, exponential moving average is averaging of the model parameter.
Yes, yes, yes. Okay. Finally, we have our main result. So we run reinforcement training over the Code Llama 34B model, which was the state-of-the-art coding model at beginning of this year. We run reinforcement training over all the public available coding data set and compare that with AlphaCode. So you can see that compared with AlphaCode, we can have like 6% improvement accuracy on the test set. So which is I think a very big improvement. So a few takeaways. We'll have some suggestions. So one suggestion is when the ground truth reward signal is available, for example, like math, coding, something else like this, you don't have the reward problem. So we really suggest you can run PPO compare with DPO. And a properly configured PPO can be really strong. Okay. Otherwise, if you have a very noisy reward model or just like running PPO can be very expensive, we'll suggest DPO iterative DPO. And iterative DPO can be a very competitive baseline. So it's easy to implement and relatively cheap. Yes, but but you always remember that PPO is stronger, but it's just more expensive to run. So when you can have a trade-off between the cost and the final performance. Okay, a few suggestions. So if you apply DPO, we suggest one, perform the additional SFT if you need. So you need to carefully annotate the data set. And also we will really suggest to run iterative generation of new answers and new feedbacks if you have a reward model available. Finally, if you run PPO, we suggest a large batch size. We suggest advanced normalizations, and we suggest the exponential moving average of reference model. Okay, that's our suggestion. So here is our answer to the first question, algorithm side, right? So we suggest a PPO if you have sufficient resources. And also if no, it will suggest iterative DPO, which is the best alternative of lightweight computation. Okay, this is the first part. Any questions?
Yeah, I'm very skeptical about the method part. So if you could go to the example part, when you talk about the ratio of the DPO, that makes the, yeah, I feel like that is not the issue of the DPO. That is because when it's trying to minimize the ratio of the positive sample over the reference, that is because this comes from KR penalization. So the issue really comes from the KR penalization. So if using like this thing will cost all the issue, then means that we should not use secure realization in the PPO part. For example, some better organization like Maximal, mean discrepancy should be the better one. But if you use the PPO part, then I think it should have similar issue because care divergence still optimized against the ratio of the IC double parameters.
Can you repeat the question?
Let me summarize this. Correct me if I understanding is wrong. So your question is basically saying that the issue from the KL, and you think PPO should also suffer from this ratio issue.
The ratio to optimize this ratio is because we use care as the penalty rather than PPO over PPO. So I think the issue is at the care relation.
So first of all is possible. So I mean twofold. One thing is it's possible to have a better distance measure, and it probably can have a better metric. So this is one fold. So it's possible, but I mean, in any case, but I would say in this. So okay, first of all, it's possible. The second thing I think is more fundamental. I didn't talk it in a very careful way. Is DPO? If you strictly follow the DPO formulation, you have a static data set. So to any sense, is a offline estimation of the KL divergence or any probability distribution distance. So PPO is an online measurement. So this is pretty tricky. So we actually have some recent work. We're doing some measurement between basically so you can have some important sampling version of the KL divergence as well, but to reduce the variance or something. But if you really measure the KL here and the online ground truth KL, you'll find that as you run in DPO more, the difference will be keeping going up. So you have a the KL term can be, particularly in large language model, the output token is, you have a lot of very large action distributions. So it'll be extremely high variance to estimate this KL term. So that's why we'll suggest try to have an online estimation, and that's the thing. So
you mean the variance?
Yeah, the variance here it doesn't work. It's like all the tricks in reinforcement learning to reduce variance doesn't work here because LM is so large variance. Mm-hmm. Right. So that's why we suggest to run an online version.
Okay.
Yeah. Here we just stick on this formulation to try to raise a minimum example showing that all kind of trouble.
I accept that answer, but just it's skeptical about your explanation because you say ratio here makes the whole.
Let's put the longer discussion.
Okay. Yeah.
Is that just like you first around like a few rounds of DPO and then a few rounds of SFT unaccepted answer?
Iterative is basically you have a model. So you roll out. So assume you have a reward model, and then you can generate a bunch of responses, and then based on the reward feedback, have a ranking of responses, and then you can generate a contrastive data set, and then just doing that instead of having a fixed data set. So you just rebuild a data set, preference data set based on the reward model ranking.
Oh, so then which part is like, I think you also mentioned like first round some DPO and then
SFT. Yeah, SFT marginally improved, but it's better to combine everything.
But this is like two separate stages, right? You first run DPO and then run SFT.
Yes.
I don't know how this would be different because if you just directly inject a SFT loss here.
You can just like it's just from our experience, basically if you combine two loss, it's better just to have two phase, just like empirical, but you can combine everything together. It's okay. Yes. Any more questions? Okay. Yeah, too many slides. Okay, so this is the answer to the first question, and then we'll move to the second part. How to make best use of the reward model if you have one. Okay. So this is our ongoing paper called On Designing Effective Reinforcement Reward at Training Time for Language Model Reasoning. So before we start, we have a definition of the reward we talk about in this talk. So suppose we have a language model reasoning problem, we have a mathematical question, and we have a generated answer, right? And there are two kind of reward. One is we call it success reward, which is a verifier giving you whether this answer is correct or not. So this one is we assume we have a verifier. And for mathematical problems, this verifier is kind of okay to achieve. You can assume you have an oracle response of whether this answer is right or not. And then in addition to that, we have a learned reward model, which is basically give you a partial feedback of whether this response is good or not. So the reinforcement objective will have a few parts. The first part is the KL divergence. You have a success reward, which is we call it correct or not. And then you have a cumulative reward part here. So in this talk, we talk about the learned model for the cumulative reward part. So what kind of reward that we can learn that can give you additional training signal and benefits in addition to the sparse successful reward. So this is what we talk about. Okay, so this is a definition. Any question here? Okay, so for this definition, and in the literature, there are two kinds of reward learning scheme. One is called outcome supervised reward. The other one is called procedural supervised reward. So the outcome supervised reward is basically you learn a function based on whether trajectory is good or not. And this function will give you estimation of how likely this trajectory is to be correct or not. So typically for outcome supervised reward, this reward term is only added to the final step. So it's like a final step additional reward shaping term. But for the supervised or procedural supervised reward, which is originally proposed by OpenAI and promoted by OpenAI, it's basically learn a stepwise reward shaping term. So it will give you a stepwise reward term at every time, every step. Okay, so this is like the most popular reward term. And also, you know, in the existing literature, most of the evaluation of this reward functions are evaluated at inference time search. So typically people will do some inference search or best of n search, and then use the reward model to vote for the best answer, and then to evaluate whether this reward model could give you higher test time inference accuracy. So the natural question will be, okay, with this inference time good, so with this reward, which is good at inference time, are these same insights also applied to training time, right? So can we also, so suppose we have a reward model which is good at inference time, good at best of n votes. Are these models still a good one for reinforcement training? Okay, so this is the question we have. So in order to evaluate the training effective, so we consider three kinds of different reward strategies. One is the sparse reward one, which is only have the successful reward. Second one is a simple combination of successful reward and outcome supervised reward, which is you have an additional term in the final step in addition to the successful reward. Third one is the step level procedural reward model. So you, instead of the correctness reward, you also have for every step, you get a reward feedback, a reward signal from a procedural reward, the PRM. Okay, these are three. So we have very naive combination of these three different models, different reward strategies, and we run a training and to see how it happens. Okay, so we run some training on the 1.5B base model on the mathematical, on the mass data set. So for the outcome reward model, so you can see all this like green curve and yellow curve. So the outcome reward model is only give you supervision on the final step. So it really accelerates the training process in the beginning, but then it's just saturate, will eventually have the similar performance as sparse reward. This is kind of intuitive because outcome supervised reward is learned from the final successful signal. So it shouldn't give you like any additional signals other beyond the successful signal or not. But interestingly, a surprising phenomenon is that we find that for procedural supervised reward, the model can collapse. It just directly failed with, just crashes. So this is very surprising because a lot of people feel that, procedural reward give you a lot of additional supervision signals, and it give you fine-grained guidance on each step. So this should give you better performance, but why it just fails? So this is something we want to dive in. Okay, so why? So the question is, why training just collapse with PRM directly when it directly serves a simple combination of successful reward and procedural reward, right? So we draw a sample. So we draw a sample of the sample output generating trajectory of the PRM trained model. So in this model it looks okay because it basically solved the problem in 5 steps. This is a correct output, right? So in the 5 steps, solve the problem. But interestingly, we find that the model output a lot of something like, nothing or ready or even emoji, after this problem is solved. So, and this this trajectory have a very high reward, procedural reward. So the question is, there must be some issues, right? But what are the fundamental issues of procedural reward? So we just further dive into this phenomenon. We find 2 observations. The one observation is that we find that PRM will tend to give you positive reward on seemingly correct but unnecessary steps, right? So we draw a correct sample, right? This is a correct sample. But if we replace each step or inject some steps with some other step, like just say down, or just repeat the answer, or just do a random equations just seemingly right, the PRM will still give a positive answer. So in this case, right, so the LLM will find a reward hacking strategy by simply repeating this nonsense or unnecessary steps. It can give higher reward, right? So this is one the intrinsic bias of PRM, so which leads the language model to generate longer responses. So this phenomenon won't be that severe at inference time because you never train this model. But if you put this reward model in the reinforcement training process, this bias will be amplified and reinforced and eventually give you a crash. Okay, so this is the first observation. And the second one is more tricky. Okay, this is the second one. So we have some reward misspecification issue. So consider this example. We have a prompt. We have 2 responses and both responses are wrong. So they're wrong. But for the left one, you only wrong at the final step. So the first 2 steps are correct. On the right one, every step is wrong. So let's think, which trajectory should be promoted by reinforcement training, right? Ideally, we want the left one to be promoted because it's almost right, compared with the right one. But we find that in the real reinforcement training paradigm, the right one is promoted. Why? So here's the thing, right? So you may ask, okay, PRM will give you the wrong responses. No, PRM will give you exactly the right reward scheme. So the left one, for example, the left one, PRM give you a 0.82. So so the right one have a like 0.53. So the left one, the correct partial step, PRM give you exactly a higher partial reward. But why is it not promoted? Because in reinforcement learning, we are promoted accumulative rewards. In the right one, because the trajectory is longer, so the accumulative reward is higher, right? In reinforcement learning, the algorithm promote higher cumulative reward, which is return. So in this one, although the reward, the left one is higher than the right one, but the return, the left one is lower. So unfortunately, although PRM give you the right supervision signal, the reinforcement algorithm give you the right promotion. Okay, so that's bad. So here's the thing. So here is a mismatch here. Procedural reward model give you a stepwise preferences, but the reinforcement learning promotes on return. So there's no guarantee on the preferences over return. And that's the issue. Okay, so here are 2 observations we find and try to address this. Okay, so the question is, okay, then we know these observations, how can we address this to fully utilize the PRM, PRM power for effective reinforcement training? Okay, so we have 2 very, very simple techniques called clip and delta. All right, so for clip, that's simple. Well, just like for every reward, we first subtract that with a constant to make it smaller, so that for this boundary, so this uncertain reward model with very low positive reward, we put that as a negative one, and then we upper bound it to 0, so there's no positive reward again anymore. So there's only negative reward. So high positive reward becomes 0, and low positive reward become -1. And so in this case, the whole trajectory, the whole accumulated reward is upper bounded, and there's no incentive anymore for longer sequences. So this is a very simple, very brute force technique called clip. And the second one is called delta. That is also simple. So suppose you have a stepwise reward, like R1, R2, R3, R4, and then we change that by subtracting 2 adjacent reward. So for this one, originally is R1, but we change that to R1 minus R2. And then this one is original R2, and we change that to R2 minus R3. In this case, if you think about the accumulated reward just like cancel out everything. So it becomes the successful reward plus the stepwise PRM. So assuming you have a right PRM output, then the reinforcement algorithm will also promote the trajectory with preferences consistent with the PRM. So that's simple. Okay, so in this case, if you have the delta mechanism, then the return will be consistent with the PRM model. So, okay, two very simple examples, two very simple techniques, clip and delta, right? So then we all run some experiments. Okay, so we first evaluate on some synthesis data. So we have some solution data set, and then we just manually adding some no sense step, adding some repeating step, or just repeat the final sentence. We generate a bunch of this kind of synthetic data set. So we want to see that whether the reward strategy, you have a lot of reward strategy, whether this is a good reward strategy. So even you have a lot of repetition or nonsense steps, can still give you the right reward guidance. We won't have any bias towards a long sentence, a long response. Okay, so we compare our mechanism with 2 very popular strategies. One is you put a lens penalty, or the other one is have a lens normalization scheme here. So these 2 are very popular reward strategies in a lot of reinforcement training papers. So we do that, I'll do some analysis. You can find that on the synthesis data, as the lens, the unnecessary steps increase, you can still observe a very clear trend that all this lens normalization or lens penalty, you have this trend of preference over longer sentences. But if you have delta or clip, you can see a very flat curve. And even for the clip mechanism, you can see a bias towards shorter sentences, but you can combine clip and delta so that you can have a very flat curve. We also evaluate this on some public available reward models trained by other teams. You can observe the similar phenomena. And this is the result for lens penalty, and this is the result for lens normalization. You can still see that so this is the reward model are not trained by us. So this is just like some Hugging Face available reward models. They also have this kind of problems. Okay, so this is the evaluation of synthesis data, and then we run reinforcement training. So we run reinforcement training on the Tianwen base model, and we run mass instruct training data set, and we run some large scale, some large batch size reinforcement training. So the result is, again, you find that if you really run training, if you only use outcome supervised reward, the performance similar to sparse reward training. And if you run reinforcement training with delta and clip, everything combined together, you have the best curve, right? We also compare the overall performance improvement with sparse reward only without any shaped reward. You can find that if you have a PRM with the right mechanism, and then you can have an improvement, which is the right, the blue bar, right? You can see the improvement. Also, this is our final overall table. We basically compare or train on the 7B model and 1.5B model. We have the overall the best performance. But sometimes there's for the sampling strategy, as for the sampling output, the reinforcement training give you the best output. If you consider greedy output strategy, then the improvement will be marginal. But it's still, we want to remark that we didn't use any additional training data. We didn't use any additional labeling, or didn't use any additional data filtering strategy, just reinforcement learning, given a fixed reward model, and just change the reward strategy, and you have this kind of improvement. Okay, some conclusion. And so we investigated the design choices of how to use reward model in reinforcement training. And we show you some very subtle, very tricky problems that you will encounter when you have a learned reward model in reinforcement training. And we propose two very, very simple techniques, a clip and delta. And hopefully, this is an inspiration of better reward strategies for future research. Okay, so here's our answer to the second question. Any questions?
For the training of PRM, like, the training process.
Oh, human label.
So it's
Human label.
So there's like starting from this step, like a moderating to end up with like correct.
Yeah, so there's an OpenAI released data set called PRM 800K. So it's like just human annotated data set.
Would you use clip to like transform all the intermediate reward to a negative one? So they will incentivize the model to like offer shorter answer.
Yes.
What if the answer should be long to solve the problem?
So we also suggest combine two. So combine clip and delta, then you don't have this kind of bias. So for the clip is you indeed have some bias towards shorter one. So finally the best performance get from.
How about just use delta?
It also works, but just like clip works the best. So you have a so here is the thing. So the reason is the PRM is not accurate. So I think if the PRM is accurate, it's also fine. But problem for PRM is that for some nonsense or so it's wrong, but seemingly correct step, PRM give you like still positive reward, but it's a small one. So like for example, it's a correct step, then PRM give you like 1 reward. But for some seemingly correct step, PRM will give you something like 0.1. So you need some threshold to make this uncertain reward to some negative one. So you only keep those reward above some threshold. I think this is the kind of motivation for delta, also for clip. Yeah, but if you have a very accurate PRM, I think that's okay. Yeah. Okay, good.
Yeah, we have 10 minutes remaining.
Sure. The final one is a system project, so it's pretty fast. Okay, so the final one, how to implement, right? How to implement a good one. So this is our system project. It's called a real HF. So this is basically an advertisement. So if you really want to run efficient RHF, or really you want a stable and robust and well-implemented RHF system, you can try this one. Okay. Okay, so this one is system one. So the motivation is that we really want to run distributed training of large language models, distributed reinforcement training for large language models. So for LLMs, distributed training is kind of okay because a lot of parallelization strategies, you can do a lot of fancy stuff. But for reinforcement learning, it's a bit more complicated. For example, at least we have 4 language models, right? You have actor, critic, reference, reward models. And also more importantly, if you check the workflow of reinforcement learning, you can see there are pipeline, there are dependencies. So there are 4 language models, and there are 3 different kinds of tasks. There are generation, inference, you have training, right? And each task have dependencies, and each task have different workflows. So it's much, much more complicated compared with standard large language model training. So some people may say, okay, we can do parallelizations. For example, we have 8 GPUs, and that can, for every step, I just run distributed training over all the GPUs, like generation, and then inference, and then reward, and then training, right? So this is simple to implement. But the problem is that if you have a lot of GPUs, or if you really have a large model, then you have the over-parameterization issue. So because every time you need to distribute a parameter over all the GPUs, so you have very large communication overhead. So if you really scale things up, you have a lot of overhead. So some people will say, okay, another observation is that all these pipelines, this dependency, some nodes, some tasks are parallel, right? So you can do some strategy. Basically, I keep one model in a few GPUs and keep some other models in another GPU. So some tasks can be run in parallel, right? So this is called some asymmetric parallelization strategy. So you can use some GPU for some particular language model, and then in some training phases, you can run some jobs in parallel, right? But the problem, you can see that you have a lot of bubbles in this training pipeline, right? So it's low communication. You don't need to do any communication. You can do things in parallel, but you can do jobs in parallel, but you have a lot of very high GPU utilization, a very high GPU idle time. So our solution is something in the middle, right? So we want to first, so for some kind of a task, for example, in the very beginning generation task, you should use all the GPUs. But some other phase, you should probably, some GPUs and some other GPUs should be run different tasks in parallel, right? So you need a very fine-grained parallelization strategies. And also, in order to do this, you need to distribute the model parameters on the fly. So we call this technique called parameter reallocations. So in this way, you can have very low GPU idle time and a low communication overhead if you do things in a correct way. So eventually, you have a very high throughput end-to-end training performance. So that's the high-level solution of our system. So we have implement a system called a real HF. So you input the training setting algorithms or whatever, all the things. And we have a search engine will automatically search for the most efficient training parallelization strategies and then have a runtime engine to implement that. So if for the search engine, we run MCMC sampling to search for efficient training parallelization strategies. And the runtime engine will basically just execute that searched plan. We have a lot of system implementations, but I won't go to the details. So some result, we compared with some open source, some other open source training system like OpenIHF and DSpeed Chat. You can have on like 128 H100 GPUs, and you can achieve like 1.8 to 3x speed up. And also we investigate, so we compare our search engine with some heuristic design strategies, and you can see that you have 54% or 81% improvement, particularly on very long context lengths. Also, the system can be applied to other training algorithms. You can just, different algorithm you can just implement. You can just construct the different data workflow and put it to the system. And the system can automatically adjust it to different algorithms. So that's it. And so the key idea is reinforcement is very complicated. So you really need a fine-grained parallelization strategies, and you need to do that with a particular smart strategy. And you need to do some search or some parameter reallocation strategies. So the system is called RealHF. So it's a real IHF. Okay. So you can try it out. So it's a pretty. So we use that for all the system, all the projects. So we just, if you want to run this one IHF, just try this. Okay, so this is our solution answer to the final question. So here's the thing, the solution answers to all the questions that I want to cover today. Some final takeaway messages. First one is in this talk, we will try to investigate some critical techniques for effective IL training for LLMs. So a few things for the algorithm part, we'll suggest online algorithm, or at least the iterative, try to make DPO online as much as possible, or you just run PPO, right? The second thing is reward model. So you probably you want to use procedure reward, but also you need a smart design of the reward strategy so that the procedure reward you can unlock the potential of procedure reward in training. The final one is just try our system for fast reinforcement training. And the final one is, I think for the reinforcement training paradigm, there's still a lot of open questions. For example, how to collect the prompt data set, right? How to train a procedure reward, right? And for the rollout part, you can also have a lot of techniques for generating better rollout models. We can run search or whatever. And also whether you can have a more advanced algorithm, say instead of using KL divergence, you can have a better divergence or overall design of the algorithm. So hopefully this talk can give you some inspiration to do some future research, and hopefully this is you know, a new spring for reinforcement research. Okay, thank you so much.
We have 3 minutes for questions. After that, there's another TA office hour to use this room. Any quick question?
Actually, what's your opinion about like the train PRM? There was like a higher people to enable problems that.
Well, I never so I have some insights, but I really haven't conducted a thorough study of that, so I won't comment too much. But I think the most critical problem for PRM is to figure out the first wrong step, and that's, you can't really get any simple part without asking human to do that.
For that, do you think the PRM should be like the corresponding with the
Sorry?
step? Do you think the PRM should be based on generic those responses, or should be like a separate or identical, like it's labeled by people?
Yeah, so I personally don't have a clear answer to this. My belief is it shouldn't be corresponding to any base model. That's my belief, but I don't know. Yeah.
Any other question?
I have a quick question.
No, well, I'd like to add some summary point for Yi's talk. I really enjoyed his talk. I think his talk and also his research really highlights a common theme in his research. So first is to understand the method from the fundamental level, right? The first research, the first part really highlights that. So we need to understand the mathematics, and we need to understand to have a deeper understanding. I think that's very important. So the second one is where a lot of time we care about the metric, we care about the leaderboard score. But in addition to that, we should look at the cases. I think that his second part really shows, if we look at examining more details, examining these cases, we will get deeper insight. And from those insights, we can develop better algorithm, better method. And the third point is while we are working on machine learning large language model, it's not just the machine learning. System is also very important. So if you want to learn system, you can enroll my course. Next semester, systems. So I will teach that course. Thank you. And let's thank our speaker again.